Okay, so now that we've defined how to multiply a matrix and a vector, let's get some practice. So in part one here, we've got notice 3 rows and 4 columns. So we have a 3 by 4 matrix A, and we have a vector X, which is in R4. So here we have the same number of entries in X as we have columns in A. So our first column, that's A1, vector A1. So notice I have an arrow on top. We have A2, A3 is the third column. And then in the fourth column, we're going to call that one A4. And for each of these columns, we have a scalar in the column vector X. So -1 is going to match up with A1, -2 is going to match up with A2, 5, A3, and the 2 with A4. And I just want to make a point here that notice matrices don't have the arrows on top. So we put the arrows on top of vectors or column vectors. When I'm typing them, I use bold, but if you're writing out your notes, just be sure you're clearly making a distinction between things that are vectors, things that are matrices, and things that are scalars. Okay, back to our problem. Okay, so now we've got matrix A times X, and that's going to be X1 by definition times column A1, scalar X2 times column A2, scalar X3 times column A3, plus scalar 4 times column A4. And so now we can plug in our values. X1 is -1, and we have the column vector A1. X2 is also -1, so we have a plus -1, and we have the column vector for A2. We've got X3 is 5 times column vector A3, and then we have plus 2 times column vector A4, which is 1, 9, -1. And so now at this point, we can use the operations that we've already defined. Namely, when I multiply a scalar times a vector, I multiply the -1 times everything in all of the entries in the vector. And when I add a couple of vectors, then we just add entries component-wise. So I would add the first 2 entries to get the new first entry and so on. So I am just going to use those operations to simplify this sum. And so that would give me -1 times the 2 is -2, and then we have the -1 times the -4, which gives us 5. We have 5 times 3 is 15, and 2 times 1 is 2. And we do the same for all the other entries. You get a -6, -2, plus 5, plus 18. And for the last entry, we would have a -1, plus 0, plus 5 times 2 is 10, -2. And then we just do the addition, and this gives us, in the end, a final result of 19, 15, 7. So it's worth noting at this point that the result that we get when we take the product of, in this case, 3 by 4 matrix with a column vector that has 4 entries, what we get left is a vector which is in R3. So what is left over would be a vector whose dimension is going to equal the same number of rows in our original matrix. Let's take a look at the second example where now we have the same matrix. This is a 3 by 4 matrix A. Let's see what happens if we choose a vector X, which now has just 3 components in it. So now X is sitting in R3. What happens if I take a 3 by 4 matrix and multiply it by a vector which is in R3? So again, we have the same column vectors, A1, A2, A3, and A4. And so A1, we're going to multiply by X1, which is -1, A2 by X2, and A3 by 5. And the question is, well, what are you going to multiply A4 by? We don't have a fourth scalar over here. So this matrix times vector AX, right, according to our definition, would be -1, X1 times A1, plus X2, which is -1 times A2, plus X3, which is 5 times A3, 3, 1, 2. And now we've got no value for X4, and we need something to multiply column A4 by. So we have a problem, and this operation is actually undefined. And the reason why this was undefined is we don't have the same amount of entries in vector x as we have columns in A. So A was 3 by 4, 3 rows, 4 columns. X is in R3. And when the entries in X are not equal to the number of columns in A, then we actually cannot perform this product, and this product is undefined. So let's generalize this. And what we can see is that this product, matrix A, vector X, is going to only be defined when the number of columns of A equals the number of rows of X.